So let's go ahead and get started then. So chapter 1 of the notes is on the theoretical foundations of measurement theory. So we're starting a little bit more fundamentally than the textbook does. So the textbook, you might notice, doesn't have a chapter on the theoretical foundations, but I felt that it was important to sort of slow down and go back and do that. So we're going to do that. We're going to review some of the theories of measurement that people have constructed. It's still an area of active discussion. So yeah, I think it's important to do. So measurement is fundamental to science and technology. It may seem at first to be simple because it is familiar. A length, a duration, a mass, these types of quantities are the building blocks of our scientific conception of the world. To know their actuality in a given instance is the primary aim of measurement. So that's what we're trying to do. The details are where it gets you. So there are several manners in which philosophers, scientists, and other thinkers have tried to understand measurement. Rather than rushing ahead with our intuitive understanding, we will slow down and consider these theoretical foundations. And I'm going to be relying quite a bit on this Stanford Encyclopedia of Philosophy entry by Tall. It's quite good. It's in the references section, so you can look it up if you want. It's free and open, so everybody can read it if you'd like. It's not required reading, though, just because I already require so much of you. I'm nice. I don't know. Pick a reason. So, Lecture 1, Mathematical Measurement Theory. So it sometimes is called just measurement theory. So when people just say measurement theory, often they mean mathematical measurement theory. And we're going to kind of review the main types of measurement theory, mathematical being the most prominent and first that we'll consider. And so this lecture 1.1 is on mathematical measurement theory specifically. So mathematical measurement theory concerns itself with how relations among mathematical objects, for example numbers, can represent relations among qualities of empirical objects, for example length. Okay, so that's the overall. When we get to the end of this discussion of mathematical measurement theory, we'll come back to that idea of mathematical objects representing these physical or empirical objects. For instance, summing numbers is analogous to how the quality of length of a composite object is related to the quality of length of each of the object's constituents, as is illustrated in figure 1.1. Oh, I can do this part by myself, but was there in there some that have, there should be one set that has numbers written in here, one that doesn't. Did anybody get that set? Because that one's supposed to be for me. Are there extras in the back? Yeah. Okay, so, I can do this one from memory. So, whoa. But not with that pen, I can't. So a length is a little bit, so we're going to draw this analogy to a number, okay? So for instance, if we chose 2 to represent this length, so like a length of say it's a metal bar or something, and we use 3 to represent this length, say that this is 50% longer than this one, then we would have a composite of 5 in terms of numbers. So that is this sort of analogy that we're drawing. So you can assign a number to some physical property, so some physical quality, so the length of this bar, assign a number to it, assign a number to another length, and then if you were to concatenate those two bars, put them together, end to end, you would have a new length, and it would be equivalent to summing these two numbers. So you add 2 plus 3, and you get 5. So that's kind of what we're trying to do when we talk about mathematical measurement theory, is we're trying to describe these physical qualities with numbers. Okay? All right. So, but there's subtlety here that's best considered with precise language. Let's consider some fundamental definitions of measurement theory. So you've probably heard all of these terms before, but they probably went undefined, and we're just left as intuition alone. So I think we'll do this section, and then we'll end. So we've got a couple minutes, right? Nobody's going anywhere after this. So quality, quantity, magnitude, and scale. So when trying to describe what we are doing when we measure, there are certain terms that are seemingly unavoidable. Therefore, it's worth considering some precise definitions of them. In the following, let's take the term object to mean the object of measurement. So that's what we're going to be measuring. Definition. So quality. The quality of an object is the manner in which it interacts. Okay? So that's pretty important. It's not sort of by itself, but the way that it interacts with its environment or with other objects. It is the totality of its properties, which are aspects of the way the object interacts. We can think of the properties that constitute the quality of an object as sets to which a given object belongs or not, like heavy or round. So maybe a given object belongs to the set of round objects. Immediately, however, we become suspicious that a real object can belong to such a set completely or not. So, for instance, is any real object, actually totally round? There's usually some sort of imperfection in that object. So
there's not an infinitely sized object.
I'm going to leave infinite sized objects out for now. But that's an interesting question that I don't want to try to address, and I don't want to make a pronouncement about. So fuzzy set theory allows members of a set to belong to a certain degree. So I find fuzzy set theory to be fun. Applying fuzzy set theory, you guys might have heard fuzzy logic. It's the same fuzzy. Applying fuzzy set theory to measurement theory is beyond the scope of this text, but suffice it to say that the fuzziness of membership suggests a blurring of the boundary between quality and our next definition, quantity. The quantity of an object is the amount of that which comprises it. The quantity of a finite collection of objects is the number of them. So those are the two types of things, the two ways we can talk of quantity. Note that we are already beginning to use mathematical analogies in our definition of quantity when we use a number to represent quantity. Quantity can be continuous or discrete. In the former case, it is often represented by a real number, right? Which is a continuous number. So you guys in one of your math classes probably we talked about real numbers and how they sort of fill up the whole number line, right? It's continuous, whereas rational numbers have holes in them, right? The reals do not. Maybe like a long ago math class. That's not clear. Pre-calc? Yeah. It's hard to say. But anyways, real numbers, when they define real numbers for you, usually talk about how it's a continuum. And then in the latter, when we have a discrete quantity, it is often represented by an integer. So like 1, 2, 3, 4. You're counting the number of something, you can represent it with an integer. we have used the term amount in the definition of the quantity of an object. It's a bit of a swindle, considering we have not yet defined this term. In fact, amount is not the usual scientific term. Rather, the term physical magnitude has emerged from physics. It is here that we bump against the limitation of language to define fundamental phenomena. Physical magnitude is typically defined as that which can be represented by a number about an object. So take whichever you prefer as your foundation and build up from there, but you got to start with some sort of axiom. We can't continue to define things in terms of other things forever. So we have to, the buck has to stop somewhere, and for us, we have reached it. So whichever you want to go with, you can. Thus, we have interdependent definitions of quantity and physical magnitude when describing an object. We use both terms interchangeably. So we can either talk about a quantity or we can talk about a physical magnitude. So, I got a 20 on the exam. What does that mean? Doesn't have any meaning unless you have a measurement scale for what that means. Oh, is it out of 100? You did pretty poorly. What the heck? I'm like trying to see who's walking by. Hey, it's just Chase. What the hell? So, but maybe it was out of 20. So maybe you got a perfect score. So you need to have a scale where there's no measurement. So a measurement scale is a mapping of quantities and qualities of an object to mathematical objects for representation. Okay, so that's a measurement scale. Measurement theory is hardly homogeneous, but we can think of it as being primarily comprised of considerations of, first, the nature of the objects of measurement, and two, the ways in which the correspondence between an object and its measure can be established. These are considered in the following sections, and we will consider those. I'll return to those on Friday, and we'll finish these notes. I may include some more notes for Friday. Keep posted on Slack. Get on Slack and check that out. Otherwise, welcome to the class.